Alright, ladies and gentlemen, in our last video we discussed the idea of the electric force and the charges caused by the charges that cause the electric force and the potential difference between those charges that ends up causing a motion of a particle from one place to another. Now, what is that? We know that particles will move across a potential difference, but how do we define it? We define that movement as current. Now, first, before we really delve into what current is, we must discuss something confusing about current. Well, if you look at, let's say, a positively charged object, right? And a negatively charged object. And we put our little positive test charge in between. It's going to move straight towards the negatively charged object. And because the negatively charged object is going to have a negative potential difference, well, then this is going to have a lower potential than this one, have a higher potential. So the potential difference is going to end up moving this way, right? And so that gives us a pretty simple model. Charges will always move from high potential to low potential, like they're moving downstream, right? It's a pretty nice analogy. However, when we're talking about movement of particles in current, electricity is electrons. And electrons are not positive like our test charges are. Instead, they are negative. And they will move from the negative over to the positive. They will move from the lower potential to the higher potential. They'll jump upstream like a bunch of rebellious salmon. And that just kind of destroys the whole analogy that we've been trying to do with the test charges so far. So, for the purposes of these following examples, as I explain what current is, we're just going to talk about current as in the movement of positive charge. And the movement of positive charge, I mean, the electrons are the ones that are moving, but if you think about it, because the electrons are moving here, this area becomes more positive, this area becomes more negative, so the positive charge overall moves this way. And that's how we'll be discussing current for the time being. Now, to discuss the movement of electrons in general, when they're moving through an object, objects that allow electrons to move are known as conductors, by the way. And when they are moving through conductors, these free electrons will encounter the atomic lattice, which are just a bunch of nuclei hanging around, right? The nuclei don't move, but the electrons do. And the electrons will move, their electric potential energy being converted to kinetic energy, until they bump into the lattice. And some of that kinetic energy will be lost to heat. And then they'll keep on going. And then they'll bump into something else. And they'll keep on going and bump and bump and bump. And therefore, it's not really a constant velocity that we have in the movement of the electron. It's more like somebody being violently pushed down the stairs and bouncing down the stairs, losing more energy each time, but still gaining energy by virtue of their position in relativity to the high and low potentials. So what's easier to describe is electron drift, which is basically saying the electrons aren't so much moving as they are kind of drifting along at a constant velocity. And that's just kind of the intricacies of that. So now we can define current. What is current? Well, current is the rate of the flow of the charges. It's the change of charge over time. So the change of Q over T equals I, which is the variable we use for current. And current is measured in coulombs per second, of course, or amperes, named after the famous chemist Ampere, who I don't particularly remember what they did, but I'm sure they're famous for something. And amperes are represented by A's. Pretty simple right there. However, we can also calculate current using a different method. Take, for instance, you have a certain section of wire or conductor, let's say it's copper wire, because copper wire is a really good conductor, that your electrons are moving through, right? Let's say you have N electrons per unit volume, right? Well, and all those electrons are moving at a drift velocity of v, right? Well, that means the distance that they will travel is vt, because we know that s equals the displacement equals the velocity times the time, right? So the distance they're going to travel is vt. Now, this means that all the electrons, that the volume of the section, or the volume of this entire section, is VTA, if we say that A is the area of the circle here. Because the volume of the cylinder is just the area of that circle multiplied by the length, which we've already determined to be VT. So that's the volume they're passing through. And because N is the number of electrons per unit of volume, the total number of electrons in this unit of volume will be N VTA. Right? Following me? Good. All right. So every electron has a charge of E. So if this is the number of electrons, then the charge of all the electrons in this section will be NVTA E. Right? Yeah, that's the charge. And we know that current is charge over time. So if we put that over time, the times cancel out, and you end up with current also equaling the electrons per unit volume times the cross-sectional area, which is the area of the circle created by the cross-section, times the drift velocity of all the electrons, times the fundamental charge. And that is a formula for current that will become very useful later. But for now, let us discuss resistance. Because the amount of current flowing through a particular conductor is related to the potential difference across it. Because, these electrons are going to be flowing from a high resistance potential to a low potential. There's a potential difference. A good conductor will allow a high current, a large change of charge across this potential difference. A bad conductor will have a lower change of charge. So the ratio of this, defined as the potential difference over the current, equals R, or resistance, which is measured in ohms, whose symbol is the omega, or as I like to call it, the ohm mega. Oh, I'm so funny. Yes, I know. Great puns. I make great puns. I really don't, but that's fine. Anyway, so that's the resistance. The resistance is basically how resistive a certain conductor is to the flow of current. We can also relate resistance to cross-sectional area and length. We know that resistance is proportional to the length over the cross-sectional area. Now, the constant of proportionality for this is something that we've chosen to label resistivity. So resistance equals resistivity, which is represented by this little symbol rho here, times the length over the area. You rearrange this and you get resistivity equals resistance times the cross-sectional area over the length. And the units for resistivity are ohms times meters. And if you have, say, something that has a length of 1 and a cross-sectional area of 1 meter squared, then your resistivity is going to equal your resistance. Well, for something that big with 1 meter of length and 1 meter squared of cross-sectional area, the resistance is going to be pretty small because it's so freaking huge. So resistivity is pretty low for good conductors like copper. Like the resistivity of copper is 1.72 times 10 to the negative 8 ohm meters. Pretty dang low. That being said, now we're going to discuss, why did ohm get his name on the unit for resistance? Well, that is because of his famous Ohm's law. And Ohm's law is simply a relationship between current, resistance, and potential difference. It's just that the potential difference equals the current multiplied by the resistance, which means as your resistance increases, so does your potential difference. As your current increases, so does your potential difference. If you have one of these two variables, you can calculate any of the others. However, this only applies to things we call ohmic conductors. Ohmic conductors will follow the rule. If you were to graph current versus voltage, it would look something like this. The resistance will be constant. It will follow this equation here, constant resistance as these two are changing. However, if you have a non-ohmic conductor, the graph is going to look a little different. It's going to look something like this. As the resistance changes, the reason the resistance changes is because non-ohmic conductors, a good example of one, is a light bulb filament. A light bulb filament releases a lot of heat and light when electricity passes through it. That's a lot of heat. It heats up. The increase in heat causes an increase of resistance, which makes Ohm's law just kind of go out and thrown in the trash. We don't really use it anymore when it comes to non-ohmic resistors, but we don't really tend to discuss non-ohmic resistors in the context of Ohm's law, so everything's hunky-dory when it comes to those. Now, that's it. That's all I will be discussing about current. Join us next time where we bring it all together and start talking about circuitry.